here. So a minority, good. Because there is a little bit of overlap, it's not, but it's not the same talk. Actually, it's a new one. So if you have any comments, I would be very glad to hear them. So it's like a set of different lessons, right? And the first lesson is that machine learning is really not rocket science, which at the beginning seemed not really true when I started working with machine learning. You see a lot of papers with a lot of equations. It really seems very complex, but at the gist of it, there is really not that much complexity. You have probably already seen this scheme, right? With classical programming, we take our data, we design a software which implements some rules, and then we get the answers by processing the data with the rules that we decide. With machine learning, it's different. We take the data sets, we know already the answers for these for a limited set of our data set, and machine learning gives us the rules that are needed to reply with answers given some data. And in order to show you like a bit more practical example, we are going into exactly the depth of machine learning here in a very graphical and simple way. So I'll assume that you have the task of classifying these guys, which are insects, types of, oh, sorry, I don't know what's happening. Okay. That are types of grasshoppers. That's actually two types. Let's call them the red ones or the blue ones, because saying katydid every time takes a bit of time. We don't really know anything about them, but we want to learn how to distinguish the red guys from the blue guys. And we are given some examples. So there is an expert that tells us, look, these 5 guys are red ones, these 5 guys are blue ones. And since we are, software engineers or programmers or whatever, we want to measure things to get something that we can put in our computer. So we take measurements. We measure what we call features. And these features are, for example, whatever we can measure about our insects. For example, the length of the abdomen or the length of the antennae or so on. And once we do this for all our 10 examples, 5 plus 5, we get a table like this, right? And so far it's all simple. This is what we call our training set. And given this data in the training set, for which the expert told us whether it's green or whether it's blue or red, we want to get some rules that allow us to classify a new instance. Okay, now, the data scientists especially already know how to solve this problem. They just put everything on paper, like they draw stuff. And when we draw stuff, everything becomes simpler, right? We put for like 1 dot for every one of my, let's call them instances, right, of these grasshoppers. And okay, then we see that the ones that are blue, they end up on the bottom left, and the ones that are red, they end up on the top right. And immediately everything is more clear now, right? My problem is I have a new guy. My new guy, I don't really know whether it's red or blue, but it will end up here in this called feature space. And then it's easier to understand how to give an answer. So one way to give an answer is, for example, to, like the simplest way is to just draw a line that best differentiates the blue guys from the red guys. And then the rule, the rule that comes out of machine learning is just, let's see if my new instance is on one side of the line or on the other side of the line. This line is called a decision boundary. And after all, when we train a classifier, we are basically just finding a decision boundary. So if we don't have 2 features, but instead of measuring just 2 numbers, we measure 3 numbers, then we don't have points on a plane, we have points in a space. But the concept remains more or less the same. Instead of a line, now we actually have a surface, and in the case of the linear, like instead of a line, we actually have a plane in this case. We can also see one interesting thing. Usually having more numbers, having more features, more measurements is useful. it is useful because let's assume that we don't have the measurement for the height of every one of these balls. It means that we are just measuring 2 numbers for every instance instead of 3. And then it's like projecting all of them on the ground. Then it's very possible that when these objects are in 3D space, I can find a plane that divides them, but when I project all of them on the ground, I can't find a line anymore. I have to find a more complex shape. Which is possible, in fact. And in most cases, we don't really have a line distinguishing my points. I just have, I have to find something a bit more complex. Another very important lesson, let's say it's not written down as a lesson, but it's the fact that I need to have a number that tells me, is my classifier, is my model good or is my model bad? When I do classification, usually we use accuracy. That's the fraction of the instances that are predicted correctly. Or we can also use a misclassification matrix or confusion matrix that just says, oh, look, this instance was actually a cat and it was classified as a cat. Then it will count for this cell, right? And we want to have all data on the diagonal instead of off the diagonal. Okay, so it's really important to understand these very few things, and once we do that, then machine learning just boils down to a 2-step process. The first step, we take our training set, which are training instances with known labels. There is the training process, which returns a trained classifier, which we call model. And once I have the model, I just can use it to classify new instances. And from this process, I can use this in production, or, well, in order to make sure, before using it in production, I want to make sure that my model is actually good. So in order to do that, I can use it on a few samples I didn't use for training. That's called testing set, or in other cases, validation set. And I can measure, for example, the accuracy or the misclassification metrics, so I know in advance how good or bad my model is. You would be surprised that when people actually implement machine learning, they get these basics wrong. So often I did it quite often. Okay, so the model, like this guy here, there is this a bit magical process where you say, I give you some examples, and now you come up with this guy that is able to tell you whether a new instance is one class or the other class. This process seems a bit magic. Now that you have seen this formalization in the feature space with all the points, it seems a little bit less magic. And my message here is that you shouldn't treat that model as something incredibly, like it's something that needs to be very complicated. Often, a linear model like the one that we have seen so far is perfectly fine. It's perfectly capable. In other cases, actually, I mean, it's so frequent that in practice you just use simple models, simple classifiers, and if your data is good, if your problem is not too difficult, they work perfectly well. So one very simple case is the nearest neighbor classifier. It's a classifier that you can implement in 5 lines of code or 2 lines of code if you are using Python, and you can do stuff in a bit more concise way. We could do it right now, but I have too many lessons, so I cannot go through all of them otherwise. But the point is just, when I'm given a new sample, I will just measure the distance from each one of the existing samples, and then I will reply red or blue, depending on which is the closest one. This actually gives rise to, you remember this concept of the decision boundary. Now the decision boundary is a little bit more complicated. Like, it can actually be a curve. It's in general, it is a curve. This graph, it's called a Dirichlet tessellation or a Voronoi diagram, and it's beautiful. Like you actually don't need to know that you are building a graph like this, like your classifier is internally building a graph like this. But it is just beautiful, especially if you think what happens when instead of 2 dimensions, so 2 features, you have actually 3 features. And when you have 3 features, you have to imagine the points in 3D, and all of those cells, they become these 3D shapes, which actually look a lot like bubbles, right? In a foam, when there are many bubbles, they form in space a structure like this. So in a case like this, instead of having a decision curve, instead of having a curve on a plane, you will have a surface that in general is made up by many facets. Okay, so that was the second lesson. Don't be scared of the model. And then the third lesson, and this is where, again, I see a lot of mistakes, and I did many in my time. Often you solve a problem with machine learning, it doesn't work well enough, and then you do like this guy. It's not really true. I just came up with like a conversation that summarizes many conversations with people that I had, and in the past I was on the left side, not on the right side. So the point is, you don't have a good performance from your model, and then you see, I need to use a much more complex model. Probably I can look into the literature from 2019. The best conferences had this sophisticated model. I take a couple of months to implement it, and then the accuracy will be better, right? And then you don't have the basics. Before you think about that, actually much before you think about that, you have to make sure that you have enough data, that your data is clean, that you can trust your ground truth. And in so many cases, that's not the case. When you have few data, of course, 15 instances here is a little bit excessive, but even if you have 15,000 instances, probably you shouldn't train a model with 4 million parameters, because it's a model with a lot of knobs. It's a model that can deform that surface in very complicated ways, and then it will not be able to capture what you actually care about. It will just, it is something too complex. When you train, for example, deep neural networks that are built for detecting complex visual patterns, these neural networks are built, they have been trained on millions and millions and millions of images. In most cases, it doesn't make sense to train them for much simpler problems where you maybe have much smaller training data sets. So this is like the Bible. It's a very nice book by Chollet, who is the author of Keras. Keras is a very important deep learning library. It's actually a high-level library where you can train neural networks in few lines of code. It's open source, and he has a book where he puts these 6 points. That is the usual pipeline for machine learning. And the first point, like there are mistakes you can make in every one of these points. And the first point is to define the problem that you want to solve. Usually you don't have a machine learning problem on your hands. Usually you have to solve a problem for some company, or your company has a problem, and then you say, let's maybe use machine learning, that's the right tool. But then you have to understand, what can I ask machine learning? So what are the inputs and outputs of my machine learning model? Can I acquire data for training data for this model? Because for maybe some problems, you cannot acquire training data enough. Or in other problems, they are just too complex. Like a human wouldn't be able to solve it. Probably a machine would also not be able to solve it if it's a problem that humans are good at solving usually. So as you can see, the point where you tune your model, you explore the hyperparameters, you try to test the latest, the most complex, the greatest models. It's only the last one. It's only after you have trained simple models, you have checked that everything is fine, you are achieving some performance, and only at that point you say, okay, this performance is not enough. I get 85%, I want to get 90%, otherwise my product will not work. And then, only then, you start playing with the really complex models. And most of the times you never reach that point. You just find out that the nearest neighbor classifier is perfectly good. Or a very simple deep neural network if it's an image classification problem. Then I want to show you one recent example. It's something halfway between teaching and art, maybe, to give you a message. That is the fact that one of the reasons why machine learning is hard in practice is that if you have a bug in your data or in the code that generates the data that you feed to your model, then it will be really difficult to spot that bug. And this happens all the time. The reason why it's difficult is that models will just eat your data, if your data is wrong, nobody tells you, oh, look, this data doesn't make sense. Models will try to do their best. And often their best is actually better than you expect on data that is wrong in some way. So let's talk about that. And the solution to this problem is to visualize whatever you're doing at every step. Never give for granted that your code is correct. All developers know that. But in machine learning in particular, you have to visualize every step that you do on the data in order to make sure that there are no mistakes, because nobody will tell you otherwise. So I will just go through these applications. People who were here last year, you have actually seen the whole process. There is code and a paper describing the process, data sets at this link, which is a GitHub repository. If you could just Google my name, you find it. But just to summarize, this is an exercise where we train a neural network to recognize hand gestures. And we did it a couple of years ago with rock, paper, scissors. And it's really nice because then you can take people or students and acquire data sets with them. So we go through the whole pipeline starting from the image acquisition. We have to define, okay, you shouldn't be too close, you shouldn't be too far, but the image itself can be anything you want. You can have very bright backgrounds, different lighting conditions, different colors. You can have different orientations of your hand and so on and so on. So when you decide, I want to operate on images like this, then people have to acquire training they have to acquire training data. And when you acquire training data, one really important concept is that your training data must be representative of the data that you need your model to work on in the future. So if you want your model to work both indoors and outdoors, you need to also shot images outdoors. If you want your model to handle hands that are rotated, you have also to take hands that are rotated. And sometimes this is a problem. Sometimes, for example, when we do this exercise in informatics classes, we ask, do you guys want your model to work on girls? And then, yes, of course, but we don't have any girls in the class, usually, in informatics. And then we have to think, oh, really, then maybe we can ask some girls. That's also a good answer. Okay, so when you acquire all of this data, you divide them in classes, you know which is the class of every image, and then you split it. You say, okay, let's assume I never actually seen these pictures. These pictures I leave out, right? I call it test set. The other ones, I call it training set. I train my neural network with these images, and I measure, while I train it, how good and how accurate my neural network becomes. The accuracy reaches 1 very quickly, and everyone is super happy when we do this exercise. They say, yeah, perfect. This means that my neural network has learned to classify the pictures correctly always, even if the pictures are really difficult. And then we see, okay, let's see how this network works on the test set. That's the images we left out. And when we do that, we see that the accuracy is pretty bad. And the reason why it's pretty bad is that we obtained a problem with overfitting. It means that our neural network has learned by heart. It had enough parameters to be able to memorize all of the instances in the training set. So it didn't really learn how to distinguish the concept of rock from the concept of paper, from the concept of scissors. So to solve it, we need a much larger training set. And instead of shooting the training set, we use a technique that is incredibly powerful that's called data augmentation. So if we have one image with rock, and I rotate the image 90 degrees, that's still an image with rock, right? But it's a different image. So why not to just rotate it? I can do it with code. It takes 0 time. And generate so many variations for every single image. So instead of having maybe 1,000 images that we acquired, we can have 100,000 for free. And when we do that, like this is an example, like the original image and all the variations, then we see something like that. When we train, then the accuracy of the training set, the black line, it grows, but it doesn't grow so fast. And the accuracy on the testing set, the blue line, it stays more or less like that. This makes us happy. It means that we are actually learning something that not only applies to our training data, but it also generalizes to the data on which we want to apply my model. Okay, so when we do this activity, we show that given an image the network has never seen, the outputs are usually pretty good. We like the results. We can compute the accuracy, and we see that around 80–90% of accuracy. Of course, there will be also some mistakes. And one error people make often is to think that if there is a mistake, the mistake is a big problem. Actually, sometimes the mistakes are unavoidable. This is not such a case. This is an image where it's quite clear that there is a rock here. But in other cases, that's not the case. So this is like a mistake, but it's not so dangerous because the network says, oh, I'm undecided between paper and scissors. Then it's quite okay, depending on the context, right? And then the nice thing is that once you train the model, you can apply it also very quickly. It doesn't really need a GPU or a particularly powerful hardware. And you can see the results here. What you see here on the right is they are called the internal maps of the deep neural network. That's like the processing on the images that the neural network is doing in order to find out which is the class. It's something that looks very cool from the artistic, let's say, point of view. And that's why actually our director decided in the last few months to build like an artistic installation. Maybe some of you have already seen it. Those who didn't, I suggest you just go there. We are now here, and if you go to the station, it's actually exactly below the station. Like if you go on the other side of the station from the lake, then you can enter a tunnel that passes below the station, and inside there is stuff like that. I'm not sure it's actually very visible on the screen. It's a set of ropes which have no function at all, just a visual, and a set of displays that show the internal maps that show the activations of the neurons inside the neural network that is recognizing gestures from a camera that is placed in the tunnel itself. So you can try it. There are 2 different classes. It's not for rock, paper, scissors. It's for like 3 fingers and close, like the closed fist. And then there are a couple of Easter eggs, like if you try to make bad gestures, it will probably detect it and make the screens black. And you can also make a heart with your hand. So of course, I was working on this on the technical side with Gabriele Abate, who is a researcher at the Institute. And you are like, given the job that you do, you probably know that it didn't work the day before the opening, right? We were training the models, and the models had a very bad accuracy, a very bad performance. And both me and Gabriele, we are both quite expert in machine learning, and we thought we didn't make any mistakes, but the models were not good enough. So the problem, I tell you without too much suspense because we don't have much time. is that we were training on BGR images like OpenCV opens them. But the camera that we used in the tunnel was producing RGB images. We actually visualized the data a few times, but I am colorblind, and I actually don't see much difference between these two images. And so this went, and also the models were not performing very bad. In this case, the models were quite good, where they had an accuracy of 70%, 65%, which is much better than chance, because chance would be 33% on 3 classes, right? Let's say. So the models were working, they were learning something, but they were still a bit confused by these images that we were providing, because they had a different color space. Eventually, we ended up using grayscale images, even after we found out the problem. Also because we were a bit scared that in our training set there would not be people with all the shirts with all the possible different colors, and maybe there were, black people and we didn't have actually that data in the training set. So we said, let's use grayscale, because as humans we can still see the difference. Actually, color doesn't really help a lot in that case. So probably we should use grayscale, and the network that is running right now is actually a grayscale. Okay, so the next, this is our reaction, right? When we found it, and we were 2 people, and it missed both of us for some time. Then Gabriele found the problem at some point. Then I have another lesson that is related to the previous one, that is related to also a recent work, not so recent, from 3-4 years ago that we did, that is quite fun. So when you train your models on training data. If for any reason the data on which you apply the models is different, or not necessarily because you get the color space wrong like we did, but maybe because you train on indoor scenes and you test outdoors, or you train in summer and you test in winter when the data is a little bit different for some reason, well, then you cannot expect your model to work. You should expect that your model will make mistakes. So we developed in some years ago, we developed this system with a drone that was following a forest trail. And the reason to do that was, okay, let's let this drone fly on forests and look for people to rescue. That's a very long-term objective. Of course, we are doing research. We are not really interested in arriving up to there. We want actually to ignore all of the different problems that you have to solve to actually make a real robotic system that works, right? But only focus on, can we really, from a drone, perceive which way we should turn in order to follow the forest trail? And this is an example of a difficult pattern recognition problem. This is something that sometimes fools humans as well. This is an image that, all of these 6 are images that a drone could take, and in these images, the drone has to understand where is the trail. And this is a task that puts our brain at work. Our brain has evolved for millions of years to understand images, and still these images are difficult to understand for us. The answer, if you are curious, is that on the images on the left, the trail was on the left. Here it was going up here. The image is in the center, the trail is in the center, and the image is on the right, the trail is on the right. So we want to solve this problem. We asked, can we solve this problem with a neural network? And back then, which was when we started this project, was probably 4 or 5 years ago, we didn't know. We didn't know yet the answer to this question. So we said, let's cast this problem as a 3-class classification problem. Given an image, I want to classify it. Is there a trail on the left, or a trail on the center, or a trail on the right? It's exactly like the recognizing rock, paper, scissors, right? An image as input and 3 possible classes as output. So we trained this neural network. This is just a visualization of what's going on inside the neural network. And then in the end, you remember the concept of the misclassification matrices. We computed these matrices, and we found out that the average, on average, we had an accuracy of 85%, which is really good. We probably can't get much more than that. And in fact, if you try that on humans, so humans are actually students to which we asked, please classify these 200 images of our testing set. Can you really see where is the trail going? And then they do 85% as well. So it means that 100% here is probably unachievable because there are maybe mistakes in the data, because in some cases you cannot really tell. And the result, okay, these are some examples. That's something very helpful. When you train a model, then you can apply it on your testing data. And one very interesting thing to do always is to check the mistakes and also to look at the cases where the model gets it right. So these 3 frames on top, they are frames where the trail is going straight, and our neural network is, no, actually, these are mistakes, actually. So these are trails where the neural network didn't think that the trail is going straight ahead, but in fact, there is a trail that is going straight ahead. So these are mistakes. And the ones on the bottom are also mistakes. So they are the images where there is no trail. There should be at least. The label of these images is that there is no trail in front. But the network thought that there was a trail in front. I can actually show a better video directly from here. And it's a summary video because I don't trust PowerPoint in VirtualBox. This is like the result, right? This is our drone that was actually flying in the forest. And the images that it sees in these situations are actually really difficult to interpret. Here we were following the drone with our with a backpack with a computer that was running the neural network and so on. And so here you can see the first person view of the drone, and here you can see what's happening inside the neural network that was computing the right choice. You can see here on the right these 3 boxes. They are neurons. Actually, I can show you again because that's really interesting. These 3 neurons are the output neurons of the network. It's the first one lights up when we think it should turn left. The second lights up when we think it should go straight. And the third one lights up when we think it should go right. And we also implemented this on a drone from the University of Zurich, which can run the neural network like locally inside the drone on board. And that was interesting, like that was the result that we expected. But there is a problem, actually. Let's go here. Okay. Yes, so this was the drone from the University of Zurich in which we put this neural network. The message here, the lesson, is that neural networks don't really need a lot of computational power when you use them for inference. They are expensive to train usually, but they usually can can process new data very quickly. So this was a few years ago. Nowadays we are doing the same, not for this problem, but for a different problem, on a drone that weighs 7 grams. And nowadays there exists hardware that can run neural networks at 20, 30 frames per second that are extremely small, and they use very, very little power. So in all of these things that I mentioned, there is a problem hiding somewhere. What I showed were the final results, but at some point we were in a situation like the one in the tunnel. We were there and we were really thinking, what? The models are not really working well. Why? And it turns out that, especially in machine learning, the devil is always in the details. And here the details are that the data sets were acquired with the 3 GoPro cameras mounted on the head of a guy that was walking on the trails for many hours. But our images from the drone, they were acquired with a different camera. Here the color spaces were perfectly fine, but the cameras had very different characteristics. In particular, GoPro cameras have really nice dynamic range. They can take beautiful pictures, but this camera didn't at all, which made our problem really hard. This is an example of a problem that occurs really often, and it's called domain adaptation. We train in a domain, and then we actually we want our system to work in a different domain. And most of the times that is a difficult problem, even though nowadays there are some techniques that try to help with that, but that's a little bit at the forefront of research. Last lesson, actually, I will skip the really last one, is just coming from another recent project that I did. And the lesson is that this thing of data augmentation, you remember rotating the images to generate new ones for free, is really powerful. And so I had this problem recently, and the company wanted to recognize whether the labels of items of clothing are fake or real. And the fake ones are slightly different, but it takes an expert to find out. It's not really something that you can describe to someone. And so this is the problem they had. And the problem that I had is that they had 16 shirts that they know are real and 16 that they know are fake. And the fake ones are all a little bit different from each other. So I replied, no, I can't train a classifier from 16 plus 16 examples. But we tried to brainstorm a little bit, and after some time we said, let's try anyway. So if you have 16 shirts that we know are real and 16 that we know are fake, one thing that we can do, for example, is to take, 20 pictures for every shirt. Maybe we move it a little bit. We just take the picture of the label. We move the label a little bit. We change the lighting. We change the camera. We take 20 pictures with a cell phone, 20 pictures with a normal camera. So we are doing some data augmentation already while we acquire the images, while we acquire the data. And then instead of 16, we have 320 for the real and 320 for the fake. And then we tried doing very aggressive data augmentation. So doing the rotations, actually in this case doesn't make sense because we know that the rotation is always correct, like it's always straight. So data augmentation here implies doing very small rotations, doing small perspective transformations. And also, I'm not sure you can notice that from the screen, but you can also change the lighting a little bit. You can overlay some make a side a bit darker, make a side a bit brighter. And you can also make something that is so-called elastic transformation. So you can take your images and in a program virtually deform it a little bit. And you can also decide how much. This is an important choice. This is actually a critical choice. If you deform very little, like in the left, it's helpful, but maybe not a lot. If you deform right in the middle, but if you deform too much, then you start generating some data that is unlikely that you will ever see in practice. So you have to be very careful on how you decide to augment your data. But once once we did that, these are all different examples. And you can see that the different models here on the bottom, they reply. Now you don't see the accuracy. Some of this is also a bit confidential, but we could get a really good accuracy in the end. The final lesson. I will not go into the details. I just tell you that many times you want to solve a problem with machine learning, but the problem is actually better, should be solved in some other way. And this was like a pitch for the work of a PhD in our institute who is driving drones with gestures. If you Google my name, then you can get there in case you are interested. But the point is that in that system, which is impressive, there is no machine learning. And when people see that system, they ask, that's amazing what you're doing with machine learning. But we didn't use machine learning in that case. And also often, students want to solve a problem with machine learning that actually is a problem that needs operational research, maybe, or it just needs some rules that you can definitely afford to make by hand. Then it's important to know your tools. And this concludes more or less the talk. The conclusion, the real message that I want you to have is that, first of all, machine learning is not complex. Remember this thing on the feature space, that instances are just dots. And when you move from having 2 features to 3, well, you move from a plane to a 3D space. When you move to images that have 100 times 100 pixels, you are actually moving in a space that has 10,000 dimensions, which is a lot, which is really difficult to imagine. But in the end, it's just points in a space, in a hyperspace in this case. And machine learning, like a classification is just, a classifier is just a decision boundary between points of different classes. And then the other points are that you shouldn't obsess over the models, at least not early in the development process. But instead, you should really make sure that your data makes sense. You should visualize everything that you do and know your tools. So maybe ask yourself sometimes if you really need machine learning or if it's a tool for some other technique. Thank you very much.
Thank you very much. Are there any questions?
We have time for one, I think.
Yes. No?
No question.
Oh, yes, we have a question.
We have time for one, so let's use it. So, question about the augmentation part, right? You showed stretching the images and things like that. Is that something you have to do manually before, or is that incorporated in machine learning frameworks? Or should it be?
Well, let's say you should do it in the way that is safest and takes less time to implement. So nowadays there are libraries that implement that, and you have just to write a few lines of code. One of them is called IMG AUG. It's just something you can Google. It's an open source library that just implements these things. In this, like what I showed was implemented by hand, also because these elastic transformations are a little bit problem specific. I think that nowadays you can use libraries for most of these things. They are not already implemented within TensorFlow, for example, or Keras, but you have to use other libraries most of the time, but they are really simple to use. However, the trick is that deciding which augmentations you should do is problem dependent. In some problems you can rotate, in others you can't. In some problems you can do elastic deformations, in others you can't. So it's really a matter of having the intuition. The concept is my augmented images should look like valid training data, but they should be different from the original. Right? Then you have an augmentation technique.
So you need machine learning to figure out if your input data is usable for machine learning.
That would be maybe a bit tricky. I'm sure there are papers that try to figure out augmentation techniques automatically, but I wouldn't use them, at least not until you are really expert or so.
Okay, thank you.
Thank you.
Thank you very much.
Thank you very much. Goodbye.